Hi, everyone. My name is Raquel with adtmag.com, and I'd like to thank you all for joining us. The topic of today's webcast is why distributed tracing is essential for performance and reliability, sponsored by Lightstep. Before we begin, I'd like to cover a few housekeeping details. There will be a Q&A session towards the end of today's presentation, so please type any questions that you may have in the Q&A box. Lightstep has also provided a resource that corresponds with today's webinar, so please take a moment to check that out. And additionally, this webcast is being recorded, so keep an eye out for a link in your email so you can rewatch the presentation or share it with a colleague. And now I'll pass the time over to our speaker today, Daniel Spoonhauer, aka Spoons, who is the CTO and co-founder of Lightstep, to get us started. The time is now yours, Spoons.
Great, thank you. Yeah, I'm here today to talk about why distributed tracing is essential. And maybe you already think it's essential, or you thought it was, and maybe you're not getting quite the value that you thought from it. But before I get started, I want to just give a brief introduction for myself. So yeah, I'm Spoons. I'm the CTO and a co-founder at Lightstep. Lightstep provides simple observability for deep systems, and that observability is based on distributed tracing. So whether you're trying to figure out just whether or not a deploy has worked, or you're up at 3 in the morning answering a page, Lightstep can help you get to the root cause in just a matter of clicks, easier than any other solution I think that's out there. Before I was a founder at Lightstep, I was an engineer at Google. I worked on Google's infrastructure team and as part of Google's cloud platform. And lately, I've also spent some time writing, and in fact, wrote the book on distributed tracing. I have obviously a biased view, but I think it's a great book that my co-authors and I put together, really taking you from the beginning of what is distributed tracing, how do you get started, all the way through to use cases and even where distributed tracing is going. So a lot more information than I can possibly cover today. If you're interested, please take a look. Yeah, okay, so to get started, I kind of wanted to just set some context about, what's changed, and specifically sort of what's changed in the way that we work, right? What changes led to this need for distributed tracing? And, there's a couple different parts of that, and I'm going to kind of talk a little more specifically. Some of these are things like Kubernetes and other cloud-native technology, new architectures like microservices and other loosely coupled architectures, and then finally some more organizational things like DevOps and the way that works. So I'm going to dive into that. We started off with bare metal, years and years ago. We moved from there to virtualized machines, and from there to containers. Things like Kubernetes then add a layer of orchestration and things like service discovery on top of that. And these are great. These are all sort of new abstractions, right? And an abstraction affords you the ability to forget about some of the details, right? And maybe work a little bit more quickly because you can work at a higher level and not have to worry about all of those. Of course, there's some downsides of new abstractions, right? Someone needs to understand what's going on underneath the hood. And so that creates additional sort of complexity, things that can go wrong in your system as well. On top of that, we've also changed the way that we build things. I mentioned microservices. Serverless also fits into this category, but we've decoupled our application into these smaller pieces, which is great because that's given our teams more independence. I mean, if you ask me, the only reason to adopt microservices is to give your teams more independence. And again, that's great. They can work, they can set their own schedules, they can deploy on their own. But that creates additional complexity, and it also makes it harder to see the bigger picture about what's going on, right? Speaking of those teams, the other thing that we've done is adopt a bunch of new practices in the ways that we work. So not technological change, but organizational changes. And a lot of these fall under the umbrella of DevOps, right? This is, there's a lot of ways of thinking about DevOps. Is it a culture? Is it a set of tools? To me, it's really about bringing your teams closer to their users and tightening that feedback loop so that they are, responsible from the definition, the construction, and the delivery, and the maintenance of that functionality. And that's great. That's also a way for teams to move more independently and boost that velocity. But it's also created a lot of challenges. And the way that I like to think about that is in the following. So, we've had a lot of innovation and a lot of investment, I think, on the part of many organizations in terms of how they control their systems, right? So control, I guess I mean things like Kubernetes, Helm, all the associated tools here. It could be service mesh, like Envoy, Istio. It could be other kinds of automation tools. But these are, I mean, it's sort of obvious that we'd invest in these things, right? Because you can't deploy without these tools, right? And that's great. These are things that allow us to move faster and to to really raise that level of abstraction, right? So a service team doesn't need to think about plugging in new hardware like they did in the old days. They don't need to think about even a lot of the operating system configuration. They're really in a containerized environment. It's quite small. The surface area that they're building on is also quite small. But there's another half to this circle here, right? And which is that in order to effectively control systems, you also need to observe them. And I think this is an area where we as an industry have just innovated less, and we've invested less in the kinds of tooling and the practices and education around this sort of thing. And that's a problem. That's sort of like it's like we've built a really fast car without a speedometer, right? Like we know it. I mean, we think it goes pretty fast. It feels pretty fast, but we don't really know how fast we're going. And that's, I think, one of the things that does is that puts developers in a hard position, right? Because this sort of that observation can be applied at all kinds of different levels, right? This is from making sure that you've configured autoscaling correctly, all the way up to thinking about when to build a new service, thinking about your architectural design as a whole. Those are all things where you need to understand what's happening in your system. Eventually, you'll need the tools to control them, but in order to make good decisions, you need that information. And that's really led, like I said, it's put these developers in a hard spot, and it's created a lot of stress. And in particular, it's sort of the textbook definition of stress, and I'll explain why in just a second, but this idea of stress being the idea that you have responsibility without control. Okay. And the way that that's, I think, manifest is that, with Kubernetes, each team got more control over the individual services, right? But that control is now distributed, right? And DevOps means each team has also, more control over the tools that they choose, over when and how they push new code. But each team depends on many other services now, right? So, and if you think about, one individual team, say like right at the top of this pyramid here, they can only control that one service. Right? That's the only service that they can roll back if something's gone wrong. That's the only service that they can push out a hotfix for. But the performance of that service that they're responsible for depends on all the services that are below them. So they're ultimately responsible for all of those services as well. And it's not just those services, it's the infrastructure, right? It's what's going on underneath the hood in Kubernetes within the virtualized environment. And it's managed services as well, right? Like this could be some hosted storage service or a third-party API that you're using to do, say, authentication or fraud detection, whatever those things are. The performance of the things, we've made those critical parts of our systems, and in doing so, we're now responsible at some level for the performance of those things, and that's super stressful for developers, right? So really, part of what we need to be doing here is closing the gap between that control and responsibility. And, what do we do? Well, like a lot of solutions, it means having the right data, right? It means setting the right goals for those teams. And I think importantly, it means, giving teams the right kind of ownership for hitting those goals, and when they're not, making changes in order to hit them in the future, right? And what I'm going to talk about today is really how distributed tracing is essential to closing that gap in order to give your teams back the control that they need in order to achieve their reliability and their performance goals. Okay, so what's it look like this rest of this presentation? So just to kind of draw a little bit of a map here. So I'm just going to go over some sort of fundamentals of distributed tracing. I think distributed tracing can mean a lot of things, and I want to make sure we're all on the same page. Then I'm going to talk about a really important concept in using distributed tracing, the critical path. From there, I'm going to kind of dive into a bunch of very specific use cases, even some examples from our own systems and how we've used distributed tracing. And then finally, a little bit about how we can get to that point. What kind of instrumentation do we have to do? How do we roll out distributed tracing? And from then there, I'll wrap it up. So, like I said, distributed tracing at some level, yes, it's a tool. But first of all, they're not all the same, right? So even if you've gone and you've bought one or you've implemented one, like there's really a range of functionality that they offer. And so even if you've already adopted a distributed tracing tool, and maybe especially if you're not getting all the value you expected to get from that tool, I want to make sure we're all on the same page in terms of what distributed tracing can do. Okay, so I'm going to start with a picture, or a bunch of pictures actually. This is maybe the easiest way to start with what is distributed tracing. These are all visualizations of a trace, right? This shows sort of how a request is handled from the top to the bottom of the stack, showing kind of like in a Gantt chart sort of way with time going from left to right, what happened in order to service this request. I'm going to explain a bit more in a minute, but this is really the building block of distributed tracing, right? These are the traces, but distributed tracing is going to be a lot more than that. Just for those of you that don't think in terms of in pictures, just to give you a few words to kind of chew on. So tracing is, I think, a diagnostic tool that reveals how a set of services coordinate in order to handle individual requests. It's going to be end-to-end, right? So from browser all the way to backends, to your databases, your hosted managed services, whatever you depend on. And it's going to include a lot of other data that tells you what's happening. It's not just the connections, but it's really a way of bringing all of this data about your services together, and doing that in a way that's takes a very request-centric point of view. I had a panel with the other authors of the book a couple of weeks ago, and we all kind of have a different history on distributed tracing. Some of us came from academic research side, some of us more industrial experience. And we've worked with lots of different distributed tracing systems, but the kind of common theme in all of those things, no matter how you store the data, no matter how you use it, you're really taking a request or a user-centric view of the data. And I think that's particularly important now because it's easy to lose sight with all the metrics that we could be looking at, that the ones that your users are experiencing, the ones that describe what your users are experiencing, are really the most important ones. Yeah, another way that you can think about distributed tracing is in terms of data structures. You can think of it as a sort of struct, and that's one way of thinking about it for sure. So I kind of sketched what that might look like here. You can think of the individual pieces of this trace, the spans, as kind of timed events. But again, this is really just a building block in a lot of ways. What's important is the connections between these pieces, right? So if we kind of think a little bit more carefully about what do those colored bars mean here, right? Really, the arrows that are kind of going down and to the right here, those are where we're making calls, right? We're making an HTTP call or an RPC call, across services, across hosts. And then the arrows that come back up, those represent the returns, right? And so traces are really encoding the causal relationships between the caller and callees. And that's really important because that gives us the information so that we understand, where responsibility begins and ends, and we know how to attribute failures and other issues. But as I was saying, traces are really just the building blocks. Oh, and I should mention, if you want to know more kind of about the history of this, Google put out a paper now about 10 years ago about how they used it. And this is one of my co-founders, Ben Sigelman, was the main author on this. But really, this will give you a historical context and tell you a bit about the data, kind of how to manage and store the data itself, at least at Google scale. I think one thing that's kind of missing from this is how we use it today and how in the 10 years what we've learned since then. But as I said, traces are really just these building blocks. They're the raw material of what we have. And another way you can think of that is that they're the fuel, not the car, right? They're just these structs. And if we want to compare distributed traces with distributed tracing, tracing is really the way that we extract value from that raw material, right? It's the art and science of doing so, and it's about building essentially like a product out of that information, right? And so I guess, when I talk about these use cases are really going to be what are ways that we can derive value from that raw material. Okay, so just kind of to sum up, what is distributed tracing? What are you looking for with distributed tracing? You might be thinking about a request-oriented way of observing your software system. You might just be thinking about it as a kind of data or a data structure, a kind of telemetry. You might think about it as a set of analyses that are performed on top of that data. Or you might think about it as the solutions for use cases that are based on those analyses. And really, I'm kind of here to argue that it's all of those things. If you don't have all of them, then you're not really getting the value that you should be from distributed tracing. But I think this helps to also kind of put it in context with respect to how other tools can offer value as well. Okay, so that's kind of a little bit of a crash course. Again, making sure we're all on the same page with respect to distributed tracing. The other thing that I wanted to talk about before I get into any use cases is the critical path. And so the critical path is the part of a trace that if you made it faster, it would improve the overall performance of that request, right? So in this example here, I kind of shaded part of this yellow bar. And that during that period of time, what that trace is telling us is that the yellow service is waiting on the work that's being performed by the blue one. And so during that time, we'd say that the blue service is on the critical path. Because again, if we speed up the blue one, presumably the yellow one would have to wait less. That means that the yellow one would be shorter. And again, that means that the pink one in the overall request would be completed faster. Again, there's a little bit of subtlety in how you define this in some cases, but think about it. The part of the trace that is on the critical path is the part that if you were to speed it up, it would improve the overall performance. And you can kind of take a set of traces and ask the same question, right? So how does each service contribute on average to the critical path? And this was one of the things that was really important, a really important use case at Google that's described in the Dapper paper, which is that we take all of the traces that we had for web search, billions and billions of them every week, and we'd run this analysis and say which services are contributing to the critical path. And that was then information that could be used to inform engineering work, be used to inform capacity planning and resource allocation, things like that. But it was really key to making decisions in this big organization. I'm going to talk about one sort of specific example of how that kind of can be done. So if we take kind of that critical path, and I'm just going to kind of squash it down here, right? So we're just talking about two different services, A and B. And, in this case, we're saying that, A contributes about 15% of the critical path. B does the rest. And this could be for one individual trace, or it could be for a whole set that we've aggregated in some way. And what Amdahl's law is saying is sort of two things. One is that generally, maybe this is obvious, but it's good to understand the idea here is that a 50% improvement in B is going to be better than a 50% improvement in A. But what's more important almost is that no improvement in A is ever going to improve the overall performance by more than 15%. Like there's no more juice to squeeze out of those lemons, right? And this actually happened a number of times at Google where a team that like this, service A here would go off and they'd plan, weeks or months of optimization work to improve performance. And, maybe it made a big difference on the performance of service A, of that service, but it didn't matter at all for the end user experience. And that team could have been doing something else, right? They could have been, they could have been building new features. They could have been working on reliability. They could be on vacation, right? But really, like having this information, I think, is critical to making good decisions about how teams are spending their time. Just to take a slightly more concrete example. So here, here's an API web service request, and we might think, should the security team or the team responsible for authorization be doing some optimization work, or should the payment processing team be doing that? And again, the authorization part here only takes about 42 milliseconds, whereas the payment processing takes almost 3 seconds, right? So no matter how much we optimize the authorization step, we're never going to improve the overall performance more than 42 milliseconds, which is just a drop in a bucket here, right? So this is all really kind of focusing on performance, on speed, and speed can certainly affect reliability if we hit timeouts and things like that. But just to think a little bit more about failures, if we take kind of the ideas behind critical path and apply them to thinking about failures, we can kind of come to a similar sort of approach to how we think about them. And ultimately, it's about whether or not this matters to users, right? So there's one kind of simple rule that we can apply here, which is that does an error propagate up the stack or not? That's something that traces can tell you. And if it is, then that's an error that maybe we should be looking into. But I'll probably say this over and over again, but in a distributed system, there are tons of things that are failing all the time. There's tons of things that are slow. It doesn't matter that doesn't mean that we should be fixing all of those things, because a lot of them don't matter to users, and we should focus on the ones that do matter, and then we should focus on new features and other stuff, and just not worry about the ones that are not having an impact. So like for critical path, it's really critical to understand what's happening around failures, and distributed tracing is the thing that can provide that context. Okay, so just to kind of wrap up this sort of section of things. So the critical path is critical, and that's important for a whole different variety of different kinds of work. Whether you're, like I said, planning on trying to prioritize building new features or reducing costs, or other reasons that you might want to improve performance. Once you've decided that you actually want to do that optimization, where is the right place to be looking? It might also be a super tactical and very reactive situation, right? You're responding to a page and trying to figure out what's going on. Focusing on the critical path is going to help you get to the answer that you need a lot quicker. And of course, you can look for which team to thank about slowing down your service. I feel like, in my time at Google and in my colleagues' time at other previous roles where they worked in big systems, one of the things working in cloud platform is that my team was responsible for one of these middle pieces, right? And we were constantly getting paged for performance problems that were not our fault, right? And so distributed tracing was really important for us to understand, who could we turn to figure out how it could actually be fixed, right? Because it was sort of out of our hands, right? Okay, so with that, I kind of wanted to go and dive into a bunch of use cases, and thinking about how to understand distributed systems. I'm going to talk a little bit about root cause analysis, alerting, and communication, and kind of some organizational issues that come up as well. So, first of all, one of the things that I think is really important when you have a distributed system or another loosely coupled system is understanding dependencies in that. And a lot of tools will draw a diagram that looks kind of like this, where each of the boxes or circles represents a service, and then the arrows represent some dependency or connection between them. But without tracing, even though they're drawn like this, what those tools are really showing you should look a lot more like this, right? They're just really they're showing you these pairwise connections, right? They're telling you A talks to B talks to C, but there's actually kind of a broken part in the middle of that graph, right? Where we don't understand the relationship between the calls between A and B and the calls between B and C, or those between B and D. So just to take an example, another thing that these kinds of pictures can also often show you is say, hey, the error rate's going up between D and E. I mean, I guess first of all, you should figure out whether or not your users care about that error rate, because if they don't worry about it, move on to other things. But assuming that it does matter for your user experience, you might start looking elsewhere and say, well, at the same time, we also noticed that there was a bump in the request weight between B and D. Now, without tracing, we don't know if those additional requests were the ones that were getting errors or not. We don't know if there was a timeout that was happening because of some additional load. And we don't know if there were other things that could have been affecting it, right? So maybe at the same time, the average response size went up by, say, 31% between B and C. Again, are these the same end-to-end requests that are getting these errors, or are they just different things that happen to be changing at the same time? So again, without tracing, we're really thinking about each of these connections in isolation. A talks to B talks to C, but we're not really giving in a request-centric or a user-centric point of view. It's really hard to narrow scope in these things, right? It's really hard to say, look, I only care about the requests that have errors between D and E. And there's no meaningful way to tie in other metrics that might help you explain what's happening, right? So to contrast that with tracing, we have this end-to-end context. It builds you a graph, not just a set of pairwise connections. So now we can refine that based upon properties of the requests. Say, tell me about requests that have this error. Let me look. Do they also talk and have bigger request size? Do they also have more requests than the ones that don't? And we can also link in other metrics and data logs as well, things that are going on with the system, and use the traces to provide context. Like, is an increase in, say, database latency actually correlated with the requests that are getting these errors, right? Is it that the request size is something that matters? Is it maybe we have contention for a lock or some other shared resource? If we have metrics that can describe those things, we can use tracing to actually give us a better sense of what's going on. And again, without tracing, we kind of end up with this Netflix Death Star diagram, right? Eventually, every service sort of talks in some way to every other service, and that's not useful when you're trying to actually diagnose a problem. Okay, so let's talk about diagnosing some problems. So this is actually, I stole this from some of our Lightstep's internal monitoring. So this is looking at the software that we've built in order to provide our services and product. And in this case, what I want to focus on right in here is in the middle. We have error rate, and at the very end, if you can sort of squint and see, that jumps up a bunch. And so really the question that engineers want to ask here is they want to understand what changed, right? So there was a period of time where error rate was higher, and if you look at the same period, in the hours before that, there weren't as many errors. And so what we want to do is be able to compare those requests and understand what's happening. Okay, so what do we do? Well, if we dig in and we look at those requests in aggregate, we can see that there's a particular error message that shows up in the logs. And I should say, if we go back to this original graph here, this is for a service that we call Crouton. Don't worry about what that means. But Crouton is part of our API server. And errors here do matter to our users. When we look down, if you really look carefully here, the logs that we're showing here are actually not even logs that appear in Crouton, right? So these are logs that appear somewhere else. And if we look between the red set of requests, those are the ones that had the errors, and the blue requests, those are the ones that didn't have the errors. This log message didn't appear before, right? It only appeared once we started seeing errors in Crouton. But the log message itself is from a different service that we call LiveView. So first of all, the thing that tracing has given us here is, one, we didn't have to look in the logs for Crouton at all, because it turns out there wasn't going to be anything there for us to see. And second, we didn't have to know that LiveView was the service that we should be looking at, right? So what we've done by collecting all of these traces together, by collecting the logs and metrics alongside of those things, by comparing these two sets, the sort of regression set and the baseline, we can look at differences and then call out where those differences might be, so that as a human, I can make a judgment about whether those things actually matter or not. Okay, so root cause analysis. Another way that we use this data is to make alerts more actionable. So, we use PagerDuty at Lightstep. Here's another example. It looks like where we had a bump in latency for, looks like LiveView service in this case again. And what we've done here is, this is something, again, that we might care about. We want to get a human involved in some way. But we've also provided the context for them to do that. So we've annotated the pages, not just with the fact that something has changed, but evidence that it actually has changed, right? So we can link directly to an example of a request that shows the slower behavior, right? And if we kind of dig deep inside of here, we can sort of see like there's a bunch of different sort of fan out that's happening here that looks pretty unbalanced, and there's some of those fan out requests are actually taking a lot longer than others. Now we can go address that problem, maybe think about how we're doing that batching and how we're doing that fan out to improve performance that we see. We've actually seen organizations actually take a step further and automate some of this process as well, so that maybe the latency is showing up in LiveView, but the actual cause of that might be much deeper down the stack. So why are we, waking up someone on the LiveView team so they can go and look in here and just look at the data to see it's actually further down the stack and turn around and page those people? We've actually seen, talked to folks in the community that have done exactly this. So they use traces to figure out, how to map from a user visible behavior, like a symptom, right? How to map that back to which service actually is causing those errors, right? Again, looking at how errors are propagating through the stack, and then just skipping all the services in between, right? And going and paging the ones where the error actually originated. Sometimes more than one if we're not sure, but that can save a lot of time in terms of how quickly you can mitigate an issue, and also saves a lot of sleep, right? Like not waking up an engineering team, someone on your team is a huge benefit in terms of that team's productivity the next day. So speaking of teams, this is a trace that I grabbed from one of our customers that has an app, right? And the thing that I wanted to call out here is that this span, this part of the trace is measurements that are taken from an iOS device, whereas the rest of it, I think below it in the stack, is actually something that comes from their backends, right? And there's a huge disparity in how long this request apparently took, right? If we measure it from the device side, it took more than 1.5 seconds. If we measure it from the backend side, it took 31 or 32 milliseconds, right? So like orders of magnitude difference here, right? And this is like a super common pattern. We saw this at Google all the time, where there would be two teams sitting on two sides of the same RPC or set of RPCs, and basically like both pointing at each other, right? Like, hey, it's slow. Your service is slow. What's going on? Nope, no, it's not us. Like everything, our dashboards are fine, right? And it might be if you look at even P50, maybe even P99 latency for these backend services, it might be totally fine. And maybe we're trying to make some assumption about how P99 in the iOS device maps to P99 as measured in the backends. But what tracing does is it allows us to actually understand for an individual request. We're talking about one phenomena. We're measuring it in two ways. That's fine. There's two different perspectives on what's happening. But now it's really about the measurement, right? We've agreed on what's happening. And we can see in this case, yeah, this is probably just like network error or network latency. Like this device, maybe it's, on a 3G network or something like that. And it's just taking a long time. Maybe it's a large request. That's the kind of data that a trace could also provide. But using this, using traces to really like speed communication between teams and making sure that we're all agreeing about the facts over and over again was just critical in getting teams to move forward at Google. And I think we see this a lot in the community as well. Okay. One last kind of area I want to touch in here. So thinking about how you hold these teams accountable, I mentioned things like P99 latency. Really, this is part, or you should think of this as part of a bigger framework about how to measure performance. And really, service levels are a way of doing that that's both user-centric in a way that's extremely measurable and something that you can really hold teams accountable to. So just as a little bit of a review of service levels and three-letter acronyms, so you sort of have service level indicators. Those are the things that you decide to measure. If you have a user-facing e-commerce app or something like that, latency is probably something you care about. Might also be something like conversion. If you run video streaming, maybe you're more interested in something like throughput. On top of an SLI, you build a service level objective. That's really about setting a threshold for how far you want to take this thing. That's your target. And that might be something like, keeping 99th percentile latency below 1 second. You also have to specify a time window that you care about this thing. So maybe over the last 10 minutes. And then finally, on top of that, then you can build a real contract, a real agreement around what happens if you miss that threshold. And this is where we get into things like refunds and cancellations. And for the purposes of things like distributed tracing and other monitor, usually we kind of stop in the middle of the service level sandwich here at SLOs, because that's really the thing that we can measure and the thing that we when we think about engineering teams, what we want to hold them accountable to. So how does distributed tracing fit into this? So there's sort of three important steps. First, obviously, you have to define and measure these SLOs. You hold teams accountable to those things. So, that's something that you want to review as part of an operational review, as part of a team's work over a month or a quarter. And then finally, I think the thing that's important and I think often easy to overlook is that you have to give them agency to improve things, right? Part of that is giving them the budget to do that, the time to actually make changes. And part of that is giving them the information that they need to do that. And this is, I think, where distributed tracing is really key. And, I talked about examples at Google where people would go off and spend time, optimizing things that didn't matter. It's really about giving folks the information and as I said, the budget to do that. And that's really, to me, like, ownership is like sort of these two halves, right? Like, of course, you want to hold people accountable, but at the same time, like, you have to give them the agency to actually improve things if they're missing their targets, or give them the room to do that in a way. Okay, so one way to think about all these use cases is like whether or not you're successful in using distributed tracing. And I'd argue, you are being successful in distributed tracing if you have all of these things, right? If you have the ability to do dynamic dependency mapping, if you can do, 3-click root cause analysis, if you have actionable alerts, if the alerts are going to the right people, if your teams are communicating effectively, and if you have the ability to both hold teams accountable for and also the means for them to improve their SLIs and to hit their SLOs. And what distributed tracing, the thread through all of this is really, it's about putting changes in context, right? That we don't need to look at logs that aren't relevant, right? We don't need to worry about services that aren't actually at fault. We don't need to wake those folks up if they're not responsible. If you've got these things, I think that's really like the definition of success for distributed tracing. So let's talk about how you can get there. Instrumentation is the means of getting the data out. This is really the hardest part in a lot of ways. The analysis and storage of that data, that's something that's been solved a bunch of times. There's many solutions, including the stuff that you can use to do that. But getting the data out is often the hard part. So, and this is a little bit tricky, I think, in some ways, because if you look at a lot of demos for distributed tracing, they look amazing, right? You can see all these connections, you can follow all these errors as they propagate and really hone in on things. But just, I think it's important to remember those demos, one, they took work to build and they were made to look great, right? And so I think, it's important to kind of recognize that, like, not everything has to be done in one step, right? So when you're thinking about your tracing migration, and I really discourage people from saying migration. That sounds like a thing that you're going to kind of knock out in a month or two. It's really a journey, right? It's a thing that you're going to be on for a long time and that you're going to learn a lot about along the way and through the experiences of that journey. As I said, it's not a sort of all or nothing thing. And so what I really encourage folks to do is to think about how to deliver incremental value for your organization, and then how to use that incremental value to inform the next steps of that journey, right? So, thinking about where can we derive the most business value from distributed tracing? Where are, the places where we have the least understanding? Where are the sort of bottlenecks in our application? And then, thinking about success in terms of the value that distributed tracing is providing to service owners, right? That's the kind of meta metric here. And I think that's really important in a DevOps organization, because tools in a DevOps org are always adopted bottom up, right? I mean, you can buy the best tool, but if it's not part of the the daily or weekly workflow of your teams, it doesn't matter. It's not going to get used, right? And so thinking about the value that you're providing to those teams, that the teams that own those services, is really important. I'm going to make on that note, I'm going to make kind of a plug here. I've got a few other talks kind of talking a bit more about this. So, like, how do teams get value? Kind of taking some of the sorts of use cases that I went into today and, like, really diving in deep to understand, like, how do we get that data? How do we do that analysis? How do we actually make that part of our workflow? And then how do we support service ownership on top of that? Talking about things like accountability and agency, and how to use this data to actually drive those organizational processes in thinking about documentation, automation, all the other pieces that we need in order to be effective in terms of that service ownership. Okay, so 3 easy steps, right? So when you're thinking about rolling out distributed tracing, start with a customer critical experience, right? Something that matters. Because if you build a case for distributed tracing around something that doesn't matter, it's going to be really hard to argue that you want to take the next step, right? So this often means looking at the edge. If you can get into a mobile app, great. That can be hard sometimes. So maybe look at a proxy or a load balancer. Maybe an API gateway is another way to do that. But as close to the user as you can. And then in that counter things, don't worry about getting these complete end-to-end traces. It's fine. You don't need that to start. But look to map these incoming operations to their dependencies, right? And this is really thinking back to that dependency graph, right, where I sort of described, you have these pairwise connections. If you can really map when a request comes in to where pieces of that sub-requests go back out, that'll get you a long way. And that'll actually help you map out the next steps. Where's the value in the next step in the instrumentation? Well, look at those dependencies. Look at the ones that are actually affecting those incoming operations in significant ways. And along the way, you'll build a case for service owners to adopt that. We actually have a blog post you can check out that talks about how to do this with 50 lines of code. So it's definitely, step one doesn't have to be hard, and you can actually get a lot of value from step one as well. Once you've got that, use that experience to build a kind of playbook, right? So establishing conventions that you're going to use throughout your organization, whether that's things like tags or other metadata, and thinking about what matters to your business, right? Maybe, you have different customer segments, different geos that are really important. Those can be really critical for understanding impact on users. Think about failures too, right? Like, do requests regularly cross regions? Okay, like region seems like a really important part of understanding where things might fail. Make sure that's part of the metadata that you've got in requests. And then instrumenting frameworks, libraries, shared services, anywhere where you have shared infrastructure within your application. That's a really great place to do this kind of instrumentation. It accelerates adoption. It's code reuse, right? Everybody loves that. And it'll actually enforce a lot of these conventions programmatically, right? So it's not just about documenting them, that you'll actually make those conventions real in some way. And then step three is really not about the technology at some level at all, but like I said, for tools to be successful in a DevOps organization, they really have to integrate with the daily or weekly workflows of those teams, right? And so think about how your developers and engineers are working today. Think about what matters to service owners, right? So, what are the IDEs they're using? What are the testing frameworks? What's your deployment pipeline look like? How are you building dashboards? What's in those dashboards? Thinking about what tools you're using for things like notification and alerting. Figure out how to use distributed tracing to, really multiply the value of all those things. And that's where I think you'll find that it's really essential to the way that your organization runs. I am going to make one strong pitch in all of this, which is that in this instrumentation process, you should absolutely be using OpenTelemetry or one of its sort of sibling projects, OpenTracing or OpenCensus. These are really, it's an open source project that defines an SDK, an API, and a bunch of tools for integrating with a wide variety of tracing solutions. And you'll get a lot of support through that process and you'll be able to get up and started pretty quickly. It's been integrated into a bunch of different open source projects that you might already be using. So there's zero code in that case. And this is really like a way for you to leverage community effort in terms of actually extracting the data from your application. So again, ways to sort of accelerate that process. Okay, so just to kind of sum up what I've talked about today. So thinking about distributed tracing in terms of these key use cases, right? So how do we think about what are the things, the problems that we need to solve, and how do we solve them for maintaining and improving performance and reliability? That can be things like root cause analysis. It can be things like longer term and proactive optimization that you're doing. And at the same time, as we're thinking about tools like distributed tracing, understanding how the technology and the people process within your organization has changed, right? So like how microservices and DevOps, yes, we've made teams more independent. We've also made them more interdependent, right? So now they have many more dependencies among them, yet we've distributed control. So how can our tools help solve that problem? And what I really want you to take away from this is that distributed tracing is really about putting that behavior in context, right? So when your application changes, when performance gets worse, when error rate goes up, give us some context that we can understand what's happening there. What are other logs? What are other metrics that can tell us what's going on? What are the right services that we need to be looking at? And who are the right people that can help make those changes? All right. Before we open up for questions, I just wanted to let everyone know that you can get started today using Lightstep. If you go to go.lightstep.com/request-a-demo, we have a bunch of distributed tracing and observability experts that are happy to help you understand a lot of what I've talked about today and can help you map it into your organization. And yeah, with that, I wanted to thank everybody for your attention so far and open it up to Q&A.
All right, thank you, Spoon. So just a reminder to the audience, type any questions that you have in the Q&A box right now. So our first question is asking if you could clarify the difference between a normal log with a distributed tracing log.
Sure, yeah. So this kind of gets down to the minutia of data structures at some level. I think the key difference is that in general, when we talk about sort of normal logs, there might be some structure, but they're specific to an individual service, and we don't know how that log relates to other services. Now, there's ways that, of course, you can encode information within these things, and there's sort of a spectrum here where you move towards something that looks a little bit more like distributed trace. Of these, a distributed trace is that we have the connections between services, that we understand those relationships, and that it is encoded cause and effect in the data structure itself.
All right, perfect. Next question here is asking, do you have a preferred approach for dealing with the transactions that span across multiple services?
Yeah, so I think if I understand this correctly, it's really a question around instrumentation. And, like I said, I think starting sort of from the top of the stack is important. And then really, understanding like where failures and where performance problems can occur is important. The way that I think of sort of the granularity of tracing data is you want to sort of think about what are the failure domains, right? And so if you have two services that are running on different hosts or in different containers, like those things can fail independently, and having a span, a piece of a trace from each of those that you can pull together is important. As you start talking about longer and longer transactions, I think it comes back to what your users expect, right? So maybe you're running a really long transaction that might take minutes or hours. Using tracing to describe that as one giant trace might not be quite as useful, because in the end, no human is actually probably sitting there staring at a screen for hours. There's probably smaller pieces of that transaction that individual users are thinking about. And then I think that the question is really, how do you link those traces together? So how do you use the metadata that's found in them, maybe like a transaction ID, to find other related traces, to find other logs that can help you put that bigger picture back together?
All right. Another question here is asking, what is better for an organization that is starting distributed tracking? I believe it's pronounced Jagger or Zipknight. Do you know those terms?
Yeah, Jaeger or Zipkin. Yeah, no worries. Yeah, so I mean, Jaeger and Zipkin are both open source solutions. Zipkin came out of work that was done at Twitter, which was for a long time an only internal tool and has now been open sourced. And Jaeger came out of tooling built internally at Uber and was also since open sourced. Both of those actually follow a very similar data model. Like they're both based upon the same model that was described in the Dapper paper and is used at Google. So in a lot of ways, they're not that different. There's some functionality that they provide that's different. And maybe back to my point is like, at the beginning, thinking about like, what are the use cases that you want to solve? And these different tools, they do have different functionality, even if they have sort of the same data structure at their core, and making sure that in thinking about the use cases that are important to your organization that you're solving for those. I guess the good news in this case is like you can use standards like OpenTelemetry and open tracing for both of them. And so, it's easy to switch between them in some sense. That is the way that you're extracting the data is going to be the same for both of them. And almost just to encourage you to try them both in this case. But again, you may be thinking a little bit more strategically about like what are the problems that you're trying to solve with distributed tracing.
All right, wonderful. Well, I think that's all the questions that we have for today. Spoons, do you have any closing thoughts that you wanted to share with the audience?
No, like I said, I have spent a lot of time thinking about distributed tracing, about writing about it, and obviously I'm biased, but I do think it's really important, and that there was really kind of a paradigm shift in how we've begun to build applications, and that requires a similar sort of shift in how we monitor and observe those things. And like I said, I think distributed tracing is really key to that. yeah, thanks everyone for listening.
All right, wonderful. And thank you as well, Spoons, for being with us today and sharing your expertise. And thank you also to the audience for attending today's webcast, which was sponsored by Lightstep and presented by ADTMag.com. Have a great rest of your day.